Settle into the quiet of a darkened room, and if it suits you, watch in full screen and subscribe for more work like this. The frame opens not on an image of a thing, but on the idea of measurement itself, the act of extracting a physical truth from light that has traveled longer than any human timescale can hold. There is no reach in the ordinary sense, no possibility of approach, no probe to send, no sample to collect. And yet, the claim stands, precise in its intent. James Webb has detected gravity from objects far outside our reach. To understand what that statement can mean without turning it into a slogan, the only honest path is to define detection from first principles, then to build upward, slowly, until the phrase detected gravity becomes not a metaphor, but a description of a specific chain of inference. Gravity is not a beam that arrives. It is not carried in photons that the telescope can count. Webb does not photograph gravity. It receives electromagnetic radiation, records it as time-tagged, wavelength-dependent counts, and from those counts reconstructs an arrangement of intensities, spectra, and temporal variations. Gravity appears only in the consequences it leaves imprinted on light and on the distribution and motion of luminous matter. At extreme distances, especially beyond any direct interaction, it is only these consequences that remain. Begin with the most basic operational definition. To detect something is to register a reproducible deviation from a null expectation, attributable to a cause whose alternative explanations can be constrained away. Detection is not a feeling of certainty. It is a model comparison anchored in instruments that turn physical inputs into data streams with calibratable noise. When astronomers say they detect a planet, they might mean a periodic Doppler shift in stellar lines. When they say they detect a black hole, they might mean stellar or gas orbits inconsistent with any extended mass distribution. When they say they detect gravity from far outside our reach, they are saying that the data recorded by the telescope contains patterns whose best explanation is the curvature of spacetime produced by mass energy that is not itself directly sampled, perhaps not even directly seen, but whose gravitational field affects observable photons and matter. The phrase far outside our reach is more than distance. It is causal inaccessibility in the practical sense. Webb's location near the Sun-Earth L2 point does not change what can be reached. It changes only the thermal and observational environment. The inaccessibility is set by the scale of intergalactic space, by energies required to accelerate macroscopic probes, by cosmic timescales. So the only interaction available is passive reception of light. If gravity is to be detected under these constraints, it must be encoded in light itself or in the distribution of emitters that light reveals. Now, gravity in general relativity is not a force acting in space. It is space-time geometry. Matter and energy determine curvature. Curvature governs the paths of free-falling objects, including photons. A photon's world line is a null geodesic. In a curved spacetime, null geodesics are not straight lines in Euclidean sense. They bend relative to distant coordinates. The bending is not because the photon feels a pull. It is because the notion of straightness is altered by geometry. This is not philosophy. It is a calculable statement. If the metric is g mu nu, a photon's trajectory satisfies the geodesic equation with ds squared equals 0, and the connection coefficients derived from the metric determine how the tangent vector changes along the path. In the weak field limit, where the gravitational potential phi satisfies absolute value of phi over c squared is less than 1, The metric can be approximated as ds squared is approximately minus 1 plus 2, phi over c squared, times c squared dt squared plus 1 minus 2, phi over c squared times dx squared, plus dy squared plus dz squared. From this, one can derive that light passing a mass distribution is deflected by an angle that, for a point mass m and impact parameter b, is approximately alpha approximately c squared b to the fourth gm. This factor of 4, not 2, marks the difference between Newtonian lightest particles, heuristic, and full spacetime curvature. That angle is small for a single star at cosmological distances, but it becomes astrophysically significant when the lensing mass is a galaxy or cluster, and when source and lens are aligned, so that small angular deflections translate into detectable distortions and magnifications. This is the first major route to detecting gravity at extreme distances: gravitational lensing. Lensing is not an add-on effect. It is the natural expression of geometry acting on null geodesics. Webb, with its sensitivity in the near and mid-infrared and its high angular resolution relative to previous infrared observatories, is particularly suited to study faint, high redshift galaxies, and therefore particularly suited to study lensing configurations where those galaxies are background sources. When a distant galaxy's light passes through the gravitational potential of an intervening mass distribution, its image is altered. The alteration can take the form of a shift in position, a stretching into arcs, a multiplication into multiple images, a change in apparent brightness, and a change in arrival time for variable sources. Each of these effects can be tied back, quantitatively, to the gravitational field of the intervening mass, including mass not emitting light. To keep the topic locked, it is essential not to drift into a general tour of astrophysics. The only objects of interest here are those far outside our reach whose gravity is detected, and the only mechanisms of interest are those by which Webb can register their influence. So lensing will be treated not as a scenic phenomenon, but as a measurement apparatus. The universe itself provides the lens. Webb provides the detector. In the simplest lensing geometry, define angular coordinates on the sky. Let theta be the observed angular position of an image, beta the true angular position of the source in the absence of lensing, and alpha of theta the scale deflection angle due to the lens. The lens equation is beta equals theta minus alpha of theta. The deflection field can be expressed as the gradient of a lensing potential psi of theta. Alpha equals nabla psi. The convergence kappa and shear gamma are second derivatives of psi. Convergence corresponds to isotropic magnification. Shear corresponds to anisotropic stretching. Observationally, Webb measures theta as the positions of intensity peaks and extended structures, and it measures the shapes and orientations of those extended structures. From ensembles of such measurements, one reconstructs kappa and gamma, hence PEISI, hence the projected mass distribution that created the curvature. That mass distribution might be partially luminous, partially dark. The detection of gravity in this context is the detection of a non-zero kappa or shear field that cannot be accounted for by luminous matter alone within uncertainties. But to say that in one breath hides the essential complexity. Webb does not hand you kappa and gamma. It hands you pixel values. Those pixel values are influenced by the telescope's optics, detector properties, pointing jitter, thermal background, cosmic rays, and calibration uncertainties. The route from pixel values to mass distribution is long, and at every step, gravity remains an inferred cause, not a directly sensed input. If we are to treat the topic seriously, we must stay with the chain of inference and not skip. A photon from a distant source enters Webb's aperture. The telescope's segmented primary mirror collects it, reflects it to the secondary, then through the optical train to an instrument, NIRCam, NIRSPEC, NIRIS, or MIRI. Each instrument imposes its own throughput as a function of wavelength. The photon is detected by a semiconductor array, creating charge carriers. Those are read out as counts with read noise, dark current, and gain variations. The raw frames are corrected for detector effects, flat-fielded, aligned, and combined into mosaics. Point spread functions broaden sources. Deconvolution is limited by noise and by uncertainties in the PSF. If a background galaxy is lensed into an arc, the arc's apparent width and curvature in the processed image is already the convolution of true lensed morphology with the instrument response. So to infer shear or a mass model, one must model the PSF and the intrinsic source morphology, or marginalize over them. In practice, strong lensing systems are modeled by fitting parametric or flexible mass models to reproduce observed multiple images and arcs. Webb's advantage is that it can see faint structure within arcs and detect multiple counterimages at wavelengths where dust obscuration is reduced and where high redshift sources are brighter relative to optical. More internal structure yields more constraints. Knots, star-forming clumps, and brightness gradients can be matched across multiple images, tightening the mass model. Tightening the mass model is tightening the inferred gravitational potential. That is the observational meaning of detecting gravity. Narrowing the posterior distribution over the lens potential parameters, making the curvature field not just plausible, but measured. Yet the user's topic says, James Webb just detected gravity from objects far outside our reach. In many public-facing descriptions, that phrase is attached not to ordinary lensing by foreground galaxies, but to events in the early universe, perhaps massive structures, perhaps extremely distant galaxies whose gravitational influence is inferred through lensing of even more distant light, or through dynamics encoded in spectral lines. To avoid invention, we can treat the phrase generically because the physical meaning is the same across cases. Gravitational influence is read from light. There is a second major route besides lensing: gravitational dynamics as inferred from motion. Motion is measured through Doppler shifts and through spatially resolved kinematics. Webb, via NIRSPEC and NIRISS, can obtain spectra of galaxies at high redshift. Spectral lines, emission lines from ionized gas, absorption lines from stellar atmospheres, appear at wavelengths shifted by cosmological redshift and by peculiar velocities within the system. If one can spatially resolve different regions within a galaxy, one can measure velocity gradients. From those, one can infer the mass required to produce the observed velocities under gravitational equilibrium assumptions. Even when not fully resolved, line widths encode velocity dispersions, which, with size measurements, can yield dynamical mass estimates via the virial theorem, properly interpreted in relativistic cosmology, and with attention to anisotropy and non-equilibrium effects. The crucial point is that gravitational detection here is again indirect. Gravity shapes orbits. Orbits shape velocity distributions. Velocities shift spectral lines. Webb measures line profiles. The link is physical law, not metaphor. Write it explicitly. Consider a system with characteristic radius r and velocity dispersion sigma. For a bound system in virial equilibrium, 2k plus u equals 0, where k is approximately 21m sigma squared and u is approximately minus rgm squared up to structure factors. This gives an order relation m approximately gr sigma squared. In detail, one must include geometry, anisotropy, and projection effects. The constant of proportionality depends on density profile, but the dependence on 1 over g and on sigma squared is fundamental. Higher velocities at a given size imply larger mass, hence stronger gravity. If Webb measures sigma from line broadening and r from imaging, it constrains m. If luminous mass inferred from stellar population synthesis is insufficient, then additional mass is implied. That additional mass can be dark matter or other mass components. The detection of gravity is, in this context, the detection of a gravitational potential depth implied by kinematics. The objects producing that potential may be too far to reach. The inference is made solely from photons. But there is more subtlety, and the topic demands escalating complexity without simplifying. The term detect gravity could also refer to gravitational time delay effects in lensing. When a variable source is lensed into multiple images, each image corresponds to a different geodesic path through spacetime, with different geometric path length and different Shapiro delay due to gravitational potential. The arrival times of photons differ. If the source varies intrinsically, like a quasar or a transient, one can measure a time delay between images. That time delay depends on the gravitational potential and on cosmological distances. Webb can monitor infrared variability with sufficient precision for certain systems, or contribute with high-resolution imaging to identify images and structure, while other telescopes measure light curves. In some cases, Webb itself can provide time series data. The detection is again gravity's imprint on timing. Spacetime curvature changes the coordinate time of arrival. Formally, in lensing theory, the time delay surface t of theta is proportional to t of theta is proportional to CD delta, t open parenthesis, 21 absolute value of theta, minus beta close parenthesis squared minus psi of theta close parenthesis, where d delta t is the time delay distance combination of angular diameter distances. Differences in t between images yield measurable delays. The potential term psi is directly gravitational. It is the projected potential scaled by distances. Measuring time delays is literally measuring how gravity affects time, but even then, Webb is not measuring gravity directly. It measures flux as a function of time and associates features between images. Now step back and refine the phrase gravity from objects far outside our reach. In general relativity, gravity propagates at finite speed in the form of changes in the metric. But for most astrophysical systems in quasi-static configuration, what is relevant is the gravitational field as encoded in the metric along the photon path at the time of traversal. For a lens at redshift ZL, the relevant curvature is at that epoch. The photons we receive now carry an integrated record of the metric they traversed, including the lens potential. The object whose gravity is detected is thus not interacting with us now in a Newtonian instant sense. We are receiving a delayed record of its gravitational influence from the past light cone. But this statement remains within the topic because it clarifies what it means to attribute gravity to a distant object. It is to infer properties of the metric at the lens redshift that best explain present observations. No reach is required. Causal connection via light is sufficient. The central conceptual shift is that Webb observes consequences rather than forces. Force is an operational concept tied to acceleration of test masses. Webb has no test mass in free fall near the distant object to measure acceleration. Instead, it uses photons as test particles. Photons respond to curvature by following geodesics. Their paths, frequencies, and arrival times encode curvature. So, in a strict sense, Webb detects gravity by detecting deviations in photon behavior relative to a fiducial spacetime. But to say deviations relative to a fiducial spacetime requires specifying the fiducial model. In cosmology, the baseline is the Friedmann-Lemaitre-Robertson-Walker metric, homogeneous isotropic expansion. In that baseline, light propagation is characterized by redshift distance relations and by smooth geodesics. Gravity from localized objects appears as perturbations, potentials phi and psi in the perturbed metric. Lensing and time delays arise from these potentials. Webb's data analysis implicitly compares observations to predictions from FLRW plus perturbations. Detection means the perturbations are constrained. At this point, complexity can deepen by distinguishing three related but not identical notions: measuring mass, measuring curvature, and measuring gravity. In Newtonian terms, gravity is acceleration field g equals minus nabla phi. In GR, the gravitational field is encoded in connection coefficients and curvature tensors. Lensing is sensitive primarily to combinations of metric potentials integrated along the line of sight. Specifically, the deflection angle in weak lensing involves the transverse gradient of the lensing potential, which is the line of sight integral of phi plus psi in conformal Newtonian gauge, divided by c squared, weighted by distances. Thus, lensing measures not mass directly, but the effect of mass energy on metric potentials. Under standard assumptions of GR and stress energy, those potentials relate to mass distribution via Poisson-like equations. But the observational quantity is the shear field. So when someone says Webb detected gravity, the precise meaning is that Webb measured an observable, shape distortions, multiple images, time delays, velocity dispersions, whose dependence on phi and psi is known, and that the data require non-zero potentials attributable to distant objects. The distant objects might be galaxies, clusters, or compact objects. They might be at redshifts where their light is faint, but their gravity is detectable because it acts on other light, often from even more distant sources. Now, what does it mean for gravity to be detected from objects far outside our reach in a way that feels new, just detected? One plausible interpretation is that Webb's sensitivity is enabling lensing and dynamical measurements of earlier, fainter, more remote structures than previously possible, moving the gravitational detection frontier deeper into cosmic time. The novelty is not that lensing exists, but that the set of objects whose gravitational potentials can be constrained has expanded. Webb can observe faint, high redshift galaxies and their lensed morphologies. It can identify candidate lenses and sources. It can resolve fine features. That turns previously speculative gravitational inferences into measured ones. But again, to keep rigor, the documentary must avoid grand claims and instead remain with mechanisms. So continue by making the mapping from objects outside reach to measurable reality explicit in the language of information. A distant mass distribution influences the phase space distribution of matter around it. That distribution determines where stars form, where gas emits lines, and how galaxies align. But Webb does not see phase space, it sees light. Light contains information in at least 4 dimensions: 2 spatial dimensions on the sky, one spectral dimension, wavelength, and one temporal dimension, time. Each of these dimensions carries distinct gravitational signatures. In the spatial domain, gravity can create multiple imaging and distort shapes. In the spectral domain, gravity affects velocities and potential wells, producing Doppler shifts, gravitational redshifts, and broadenings. In the temporal domain, gravity affects timing, time delays, and lensing-induced magnification variations as relative motions change alignment. In the structural domain, gravity shapes matter distributions that Webb resolves. The sizes and profiles of galaxies, the clumpiness of star formation, the separation of components in merging systems, and the geometry of arcs. The phrase Webb detects gravity is thus shorthand for Webb measures patterns in these domains that, under physical law, imply a gravitational potential. Nothing else is meant. The telescope is not a gravimeter. It is an observer of light whose behavior is altered by the metric. Return now to first principles of how a telescope measures light. A telescope is a linear system to first approximation. The observed image is the convolution of the true sky brightness with the PSF plus noise. The PSF is determined by the aperture, wavefront errors, and instrument optics. For a segmented mirror like Webb's, diffraction produces characteristic spikes in structure. Calibration and deconvolution can improve resolution, but cannot create information beyond what the instrument encodes. Therefore, gravitational inference must rely on features above the resolution and signal-to-noise thresholds. This is why high angular resolution matters for lensing. Arcs may be thin, multiple images may be close. Separating them requires resolution. Similarly, measuring galaxy sizes r for dynamical mass requires resolving them. Spectroscopy requires sufficient S and R to measure line widths. Thus, the detection of gravity from extremely distant objects is not only a triumph of physical law, but of instrument sensitivity and stability. The gravitational signal is often subtle. It is an imprint on light that could be mimicked by instrument artifacts if not carefully controlled. So, detect implies that systematics have been addressed. Consider weak lensing. In weak lensing, shear distortions are at the percent level. Measuring them requires averaging over many galaxies because each galaxy has an intrinsic shape. The gravitational shear is extracted statistically. Webb can perform weak lensing in infrared, but its field of view is smaller than some wide surveys. Its strength is deep imaging of smaller areas. In deep fields, it can measure shapes of very faint galaxies at high redshift, extending the source population for lensing. That allows probing mass distributions at earlier times. The objects whose gravity is detected might be structures that are themselves at moderate redshift, but lensing very high redshift sources, or structures at higher redshift, where previously there were insufficient background sources to measure shear. Weak lensing formalism connects observed ellipticities to shear gamma via E approximately EINT plus P gamma, with PA responsivity. The measured shear field is related to projected mass density via kappa, and kappa is related to surface mass density sigma over critical density sigma psi RIT depending on distances. Kappa of theta equals sigma CRIT. Sigma of theta, sigma CRIT equals 4. Pi GC squared DL DLS DS. Here, DL, DS, DLS are angular diameter distances to lens, source, and between them. Notice G appears explicitly. The gravitational nature of the effect is not decorative. The conversion from observed shear to mass density involves 1 over G. To detect gravity is to detect non-zero kappa, hence non-zero sigma, hence a gravitational field capable of producing the observed distortions. In strong lensing, the constraints are not statistical but geometric. Multiple images satisfy the lens equation. The Einstein radius theta e provides a mass scale. Theta e equals c squared 4 gm dl ds dls for a point mass, generalized to extended lenses. Measuring theta e from image separations yields m within the Einstein radius. Webb's images can measure theta e with high precision. The object whose gravity is detected could be a galaxy whose own light is faint or obscured. Yet the Einstein radius reveals its mass. In some cases, the lens might be a dark halo with little luminous counterpart, detectable primarily via lensing. In that case, the phrase detected gravity is almost literal. The object is detected not by its emission, but by its gravitational influence on a background source. Webb, by revealing the background source and its lensed morphology, enables the detection of the lens. This brings us to a core meaning of the topic. Gravity can reveal objects that would otherwise remain unseen. But we must treat this carefully. Webb does not conjure unseen objects. It constrains mass distributions that best explain data. The inference could be degenerate. Different mass profiles can reproduce similar lensing, especially with limited constraints. Breaking degeneracies requires more data, multiple sources, extended arcs, stellar kinematics of the lens, or external information. Webb contributes by increasing the data richness, better resolved arcs, more detected counterimages, spectra of lens and source to pin down redshifts and thus distance ratios. Redshift matters. The lensing geometry depends on angular diameter distances, which depend on redshifts. If redshifts are uncertain, mass inference is uncertain. Webb's spectroscopy can measure redshifts through emission/absorption lines in infrared, where high redshift galaxies' rest frame optical lines appear. That reduces uncertainty in D ratios, tightening sigma crit, tightening mass. Thus, Webb's gravity detection is not only imaging, but also spectroscopy. Now, to escalate complexity without leaving the topic, refine the notion of objects far outside our reach to include not only lenses, but also sources whose own gravity might be inferred. How can the gravity of a very distant galaxy be detected? One way is through its internal dynamics and mass profile inferred from kinematics and size. Another way is through its effect as a lens itself on even more distant sources. A very distant galaxy could act as a lens for a background source at even higher redshift. That would be a detection of gravity from an object deep in cosmic history. Webb's sensitivity to early galaxies could reveal such high redshift lenses, which were previously hard to find because both lens and source were faint. In that scenario, gravity from an early galaxy is detected by its lensing action. The object is far outside reach, not just in distance, but in time, yet its mass bends light. But in any lensing configuration, the observed effect is a mapping between source plane and image plane. That mapping is described by the Jacobian matrix A equals partial theta, partial beta equals open parenthesis, 1 minus kappa minus gamma, 1 minus gamma, 2 minus gamma, 2, 1 minus kappa, plus gamma, 1 close parenthesis. The determinant det A equals open parenthesis, 1 minus kappa, close parenthesis squared minus absolute gamma. Absolute squared gives magnification mu equals 1 over det A. Near critical curves where dTA approaches 0, magnification becomes large and arcs form. Webb can image near critical structures sharply, providing constraints on where dTA vanishes. Those loci are direct geometric manifestations of the gravitational potential's second derivatives. In other words, Webb images the places on the sky where the curvature-induced mapping becomes singular. That is an observational signature of gravity that does not rely on seeing the lens's light. Now, consider an even more refined gravitational signature: microlensing and substructure lensing. A smooth lens model may reproduce large-scale arcs, but small-scale mass clumps, such as dark matter subhalos, can perturb images. They can create flux anomalies, small distortions, or additional tiny images. Detecting such perturbations is detecting gravity from small mass clumps, potentially invisible. Webb's resolution and infrared sensitivity can help measure flux ratios and structures in lensed images, potentially constraining subhalos. Again, gravity is detected from objects beyond reach and beyond direct emission. The mathematics of substructure lensing can be stated as perturbations to the potential. PSI equals psi0 plus delta PSI. The perturbation alters image positions and magnifications. If delta psi is due to a subhalo of mass m at some projected position, the induced deflections scale with m inference involves fitting models with and without subhalos and comparing likelihoods. Detection means the posterior probability of non-zero m at some location is significant given priors and systematics. At this stage, the documentary must keep returning to core mechanisms while deepening. The core mechanism is curvature affects photon propagation. We have described bending and timing. There is also frequency shift due to gravity, gravitational redshift. In a static potential, a photon climbing out loses energy. Delta nu over nu approximately delta phi over c squared. In cosmological contexts, gravitational redshift is typically small compared to cosmological redshift. But in deep potential wells like clusters, it can be measurable statistically. Webb's spectroscopy could, in principle, contribute to measuring gravitational redshift effects in certain contexts. But the main gravitational signatures in Webb data are lensing and dynamics. Still, gravitational redshift is an instructive mechanism because it demonstrates that gravity imprints on wavelength, not only on direction. Detection would involve measuring systematic shifts in spectral lines relative to expectations. Yet, at extreme distances, distinguishing gravitational redshift from kinematic and cosmological components is difficult. Therefore, in most practical Webb gravity detections, wavelength information is used to determine velocities and redshifts for geometry and dynamics, rather than to isolate gravitational redshift. Return again to the phrase detecting gravity observationally. Observationally means by collecting photons, not by measuring acceleration. Gravity is detected when the statistical distribution of observed photons in angle, wavelength, and time cannot be explained without including spacetime curvature from mass energy distributions. This is a statement about model necessity. There is a danger here to drift into abstract epistemology. Avoid that. Keep it physical. The measurable effects are real. Arcs on the detector, line broadenings in spectra, delays in variability. These are not interpretive. They are pixel-level patterns. Gravity enters when those patterns are mapped back to source properties, and the mapping requires curvature. In a strong lensing arc, for example, one can attempt a no-lens explanation. Perhaps the arc is a peculiar galaxy morphology. But if the arc's curvature is concentric around a foreground object, if there are multiple arcs at consistent radii, if there are mirrored features in separate images, and if the inferred source plane morphology becomes compact and plausible only after lens inversion, then lensing is favored. Webb's high-resolution images allow identification of mirrored substructures, which is among the most compelling evidence because it ties separate observed features to a single source. That is gravity detected through topological mapping. Multiple observed images correspond to one source because geodesics are deflected around a potential, and even when the lensing mass is luminous, the difference between luminous mass and lensing mass is gravity detected from additional unseen matter. This is again strictly within topic. Gravity is detected not as an independent entity, but as a mismatch between mass inferred from light and mass inferred from curvature effects. Now deepen by addressing the distinction between local gravity and integrated gravity. Lensing is integrated along the line of sight. The deflection depends on the projected potential. Therefore, when one says gravity from an object far away is detected, one must consider that other structures along the line of sight also contribute. This is not a complication to escape into. It is central to what detection means. The data do not label which mass caused which deflection. The inference does via modeling and probability. In lensing, line-of-sight structures produce external convergence and shear. These can bias mass estimates and time delay inferences. Webb's deep imaging can help identify line-of-sight galaxies and characterize their redshifts, reducing uncertainty. Again, Webb's role in detecting gravity is to provide the observational inputs needed to separate contributions. The detection of a specific distant object's gravity requires demonstrating that the lensing signal aligns with that object's position and redshift and cannot be explained by other masses alone. This is where spectroscopy becomes decisive. If the lens galaxy's redshift is measured and background source redshift is measured, then lensing distances are fixed. If additional line-of-sight galaxies are identified and their redshifts measured, their contributions can be modeled. Webb's infrared spectroscopy can measure redshifts for faint galaxies that are difficult in optical. Thus, Webb enables cleaner attribution of gravitational effects to specific objects. So far, the narrative has treated Webb as an observer of lensing effects. But there is another route. The cosmic structure in deep fields encodes gravitational growth. But describing that in general would risk drifting into broader cosmology. Keep it locked. The specific statement is about detecting gravity from objects far outside reach. That is local, particular objects whose gravitational influence is inferred. Therefore, remain with lensing systems and dynamical measurements. Now shift to the instruments again, but only as necessary for the gravitational topic. NIRCam's imaging provides high-resolution maps of lensed arcs. NIRSpec provides spectra for redshifts and kinematics. MIRI provides mid-infrared imaging and spectroscopy, useful for dust-obscured regions and for certain lines, extending the ability to characterize sources and sometimes lenses. Each instrument contributes to constraining the gravitational inference. For example, to model a strong lens, one needs the lens mass profile and the source light distribution. The source distribution can be complex. If it is mismodeled, the mass inference can be biased. Webb's multiband imaging can separate stellar populations and dust, allowing more accurate modeling of both lens and source light. Better light models reduce residuals and tighten mass model constraints. Thus, gravitational detection is improved not by measuring gravity directly, but by reducing astrophysical and instrumental nuisance uncertainties. At this point, return to spacetime curvature manifests in measurable signals. So far, bending and time delays were discussed. Add the notion of magnification bias. Lensing increases flux, allowing detection of sources that would otherwise be below sensitivity. Webb's deep surveys in cluster fields exploit this. Clusters act as gravitational telescopes. This is gravity detected because the pattern of magnification across the field is measurable and must be modeled. It is also gravity used as an instrument. The cluster's potential creates critical lines. By observing the spatial distribution of background galaxies and their apparent brightnesses, one can infer magnification. Webb images more faint sources, which enhances the ability to map magnification. The objects far outside reach might be the background sources at extreme redshift, but the gravity detected could be the clusters. Or, in some cases, the gravity detected could be from smaller scale lenses within the cluster. Notice how the phrase flips. Sometimes the distant objects are the sources, sometimes they are the lenses. But the topic insists on gravity from objects far outside reach. In lensing, the lens is the object whose gravity is detected. That lens can be very far, billions of light years. Webb can detect lensing by objects at higher redshift than previously accessible. That is likely the meaning in public phrasing. Without relying on any external claim, the mechanism remains valid. Now deepen with a careful treatment of how lensing is extracted from data. In strong lens modeling, one often chooses a parametric form for the lens mass distribution, such as a singular isothermal ellipsoid or a Navarro-Frank-White profile. The parameters include mass scale, ellipticity, orientation, centroid, and slope. One then ray traces from image plane back to source plane for a given set of parameters and compares the predicted lensed image to observed pixel data. The comparison is performed in the likelihood function, which accounts for noise covariance. One may also include PSF convolution. Optimization yields maximum likelihood parameters. Bayesian sampling yields posterior distributions. Detection of gravity is in some sense trivial because any mass model yields some gravity. The real detection is of specific features: the mass scale, the slope, substructure. The more distant the object, the more important it is to ensure that the lens model is not an artifact of assumed priors. Webb helps because it provides high signal-to-noise images of arcs, which constrain the model strongly through many pixels. Each pixel contributes information. The arc's detailed brightness distribution is a constraint on the lens' potential derivatives. This is why detecting gravity can be viewed as detecting a field, the potential psi of theta over the image plane. The data constrain PSI such that within uncertainties, the gravitational field is measured. But there is a subtlety. Lensing measures the projected mass, not the three-dimensional distribution. To infer 3D mass, one must assume a geometry or use multiple sources at different redshifts. Multiplane lensing can occur where more than one lens plane contributes. Webb's ability to measure redshifts can help separate planes. Still, the gravitational detection remains a detection of a projection. This is not a limitation to gloss over. It is the nature of the measurement. Gravity is detected as its effect on null geodesics integrated along the path. If the object is extremely distant, its own light may be weak and redshifted. Webb may detect it only faintly. But lensing does not require bright lens light. It requires mass. Thus, the gravitational field may be measurable even when the object is nearly invisible. This is one of the deepest meanings of the topic. gravity is not subject to the same detectability constraints as light because it acts on other light. But again, Webb detects only that other light. The distant object's existence is inferred from its gravitational imprint. Move now to a more mathematical expression of how curvature affects light bundles, not just single rays. The relevant tool is the geodesic deviation equation and the optical scalar equations, Raychaudhuri for null congruences. A bundle of nearby null geodesics can converge or shear due to tidal gravitational fields encoded in the Weyl curvature and Ricci curvature. In lensing, shear and convergence are precisely these optical effects. The Jacobi map relates source plane separations to image plane separations. This is a first principles statement. Gravity changes how neighboring geodesics separate, hence how images distort. In weak lensing, one can write the distortion matrix as the identity plus derivatives of the deflection. Those derivatives are line-of-sight integrals of tidal fields. Thus, when Webb measures coherent alignments of galaxy shapes, it is measuring the integrated tidal field of intervening mass. That is gravity detected as tidal geometry. Now, because the documentary must be continuous and not structured with headings or lists, the complexity must grow by returning to the same notions, geodesics, potentials, observables, each time with more detail. So return to what it means to detect gravity. In laboratory contexts, detecting gravity might mean measuring the acceleration of a test mass due to a nearby mass, or measuring gravitational waves via interferometry. Webb is not doing that. Its gravity detection is a quasi-static field detection through lensing and dynamics. Yet the word detected is still legitimate because the inference is constrained by data with quantified uncertainty. The gravitational parameters are not free narratives. They are fit to photon data. Now consider objects far outside our reach might include compact massive objects, perhaps black holes, whose gravity is detected through lensing. A black hole itself is defined by a region of spacetime with an event horizon. It emits no light, but its environment may. However, at great distances, direct imaging of horizons is impossible. Yet gravitational lensing by compact masses can be detected as microlensing events, temporary brightening of a background source as a compact lens passes near alignment. Webb can monitor infrared light curves of stars in crowded fields or of lensed galaxies. In a microlensing event, the lensing magnification is time-dependent. The timescale depends on the Einstein radius and relative velocity. The Einstein radius in physical units is RE equals C squared 4GMD SdL dLs. The event timescale TE equals RE over V perpendicular. Measuring the light curve yields TE and peak magnification, which constrain m given distance and velocity priors. For distant lenses, distances are uncertain, but the principle is firm. Gravity from a compact object is detected through a characteristic temporal magnification pattern. Webb's stable photometry and infrared sensitivity can help detect such patterns, particularly for dusty regions where optical is challenged. Again, the object is outside reach. Its gravity is detected not by collecting it, but by watching a background source's light change. That is the same core mechanism expressed in time domain. To push deeper, examine how the telescope's time sampling and stability affect gravitational inference. Photometric precision depends on detector stability and calibration. For microlensing or time delay measurements, systematic drift can mimic variability. Therefore, detection requires careful calibration. Webb's design for stable infrared observations supports precise photometry. That supports gravitational detection in time domain. Now, return to the idea of space-time curvature as measurable. The curvature tensor R sigma mu nu RHO is not measured directly. But lensing and time delay relate to integrals of potentials, which relate to curvature components. For a weak field static lens, the Laplacian of the potential relates to mass density via Poisson equation. Nabla squared phi equals 4 pi g rho. In GR, the relation is more subtle, but in the non-relativistic limit it holds. Lensing depends on gradients of phi transverse to the line of sight. Thus, by measuring deflections and distortions, one effectively measures spatial derivatives of phi, and therefore indirectly measures RRO. This is gravity detected as the presence of non-zero curvature sourced by mass density. The object is inferred because it sources the curvature. This is why one can detect gravity from dark objects. RO includes all mass energy, luminous or not. Photons interact with electrons and dust. They can miss dark matter. But space-time curvature responds to all mass energy. Therefore, lensing detects total mass. Webb, by measuring lensing, detects the gravitational imprint of total mass. However, to remain rigorous, acknowledge that lensing measures projected mass, and that the conversion to three-dimensional mass requires assumptions. Also, lensing is sensitive to the combination phi plus psi. In GR with negligible anisotropic stress, phi approximately equals psi, but in general, they could differ. Thus, lensing is a probe of gravity itself as a theory, but again, do not drift into speculative theory changes. Keep to observational meaning. Lensing measures the lensing potential. Now, bring the focus back to Webb. It is an infrared telescope, and infrared matters because high redshift galaxies' light is redshifted into infrared. This expands the accessible source population behind lenses. More sources means more constraints on lens mass distributions, meaning better gravity detection. It also allows lensing by higher redshift lenses because source redshifts can be even higher. As complexity escalates, the narrative can now treat a full inversion. Given an observed lensed image, can one reconstruct the source and lens? This is an ill-posed problem without regularization. The inversion requires priors on smoothness of source and mass. Detection of a small perturbing mass, for example, depends on whether the data demand it beyond what a smooth model plus flexible source can fit. Webb's high-resolution imaging reduces degeneracy by providing more independent constraints per arc. That strengthens the case for detecting small-scale gravity sources. There is also the mass sheet degeneracy, transforming kappa of theta by kappa prime equals lambda. Kappa plus 1 minus lambda leaves some observables invariant up to rescaling of source plane. This means lensing alone cannot determine absolute mass normalization without additional information, such as time delays or velocity dispersion. Webb can provide the needed additional information. Spectroscopy of lens, stellar velocity dispersion. Thus, Webb helps break degeneracies, making gravity detection more absolute. Write this precisely. Under mass sheet transformation, the lens equation and image positions can remain consistent while magnifications change. Time delays scale with lambda, therefore measuring time delays can break the degeneracy. Similarly, stellar kinematics provide an independent mass estimate. Webb can measure lens galaxy spectra, giving velocity dispersion. Combining lensing and kinematics yields stronger constraints on the mass profile and thus on gravity. Now, since the topic is detected gravity from objects far outside our reach, one can interpret the object as a lens galaxy or cluster whose mass profile is constrained at high redshift. The detection might include mass profile slope, concentration, substructure, gravity field properties. Webb's data enable that. At this stage, maintain the calm cinematic tone by describing the observational scene without metaphor. A deep field image, faint smudges, arcs, and points. Each pixel is a count of photons. The gravitational story is in the geometry of those pixels. The arc curvature indicates the lens center. The multiplicity of images indicates the potential depth. The color differences across bands indicate source redshift and stellar populations, allowing separation of lens and source. Spectra confirm redshifts. The lens model reconstructs a mass map. That mass map is gravity detected, but we must not summarize. Instead, revisit from a more fundamental layer. Why does a mass distribution produce a lensing potential PSI, and how does it relate to the metric? In the thin lens approximation, one assumes the deflection occurs instantaneously at the lens plane, integrating the gravitational potential along the line of sight. The deflection for a photon is alpha squared equals c squared 2 integral nabla perpendicular phi I L, with factor 2 in Newtonian potential for GR, giving total 4gm over c squared b for point mass. The lensing potential is psi of theta equals c squared 2 dLds dLs integral phi I of dl theta comma ldl. Thus, psi is a scaled projected potential. Its Laplacian gives convergence. Nabla squared psi equals 2 kappa. This connects observed distortions to projected mass density. Therefore, when Webb constrains psi, it constrains the line of sight integral of phi, hence the mass. For objects far away, cosmological distances enter. Angular diameter distances differ from Euclidean due to expansion. Webb's redshift measurements allow correct distance calculation under a cosmological model. This is not a drift into cosmology. It is a necessary element of gravitational inference because the scaling of lensing depends on distance ratios. Without distance, deflection angles cannot be translated into mass. Now deepen further. The observed redshift contains both cosmological expansion and peculiar velocities. Spectral line positions yield redshift. Interpreting it requires separation of components if one cares about peculiar velocities. For lensing, cosmological redshift suffices. Peculiar velocities are small relative. For dynamics, peculiar velocities internal to a galaxy are the signal. Webb's spectra must be calibrated in wavelength precisely to measure line widths. Instrumental resolution must be deconvolved from observed line profiles. This is again a chain of inference. Observed line profile is convolution of intrinsic profile with instrumental line spread function. Removing instrumental broadening yields intrinsic dispersion. That yields mass via gravitational law. Thus, gravitational detection depends on instrument characterization. Now, revisit the concept of objects far outside our reach can still influence measurable reality. In GR, influence is limited by causality. We observe only along past light cone. A distant object influences us by affecting photons that reach us and by emitting photons. Its gravity influences photons passing near it long before arriving here. Therefore, we can detect its gravity without any direct contact. This is the causal structure. The metric near the object affects null geodesics. Those geodesics intersect our detector now. That intersection is the measurable reality. Webb is the device that records that intersection with high fidelity. This is not speculation, it is the geometry of spacetime and light propagation. The object's gravity is a property of the spacetime region. Photons encode that property by their paths. Therefore, an object beyond reach is still within causal reach via its gravitational field acting on photons. To keep expanding, introduce the notion of lensing as a probe of mass distribution at scales smaller than the resolution of the telescope. This seems paradoxical. How can one measure substructure smaller than resolution? Because lensing is sensitive to potential gradients that can affect image properties at scales comparable to the Einstein radius of the substructure, which can be small but still produce measurable distortions if the background source has fine structure. Webb's resolution increases the available fine structure. Thus, it can probe smaller masses. Gravity is detected at smaller scales from objects not directly resolved. Similarly, time delays can measure potential differences even when images are unresolved if one can separate light curves. But typically, strong lens images are resolved. Webb helps resolve them. Continue deeper by treating noise. Detection claims depend on signal to noise and on systematic error. In lensing, shear measurement is limited by shape noise, intrinsic ellipticity, and measurement noise. Strong lensing is limited by model degeneracies and by PSF. Webb reduces measurement noise by deep imaging and stable PSF characterization. But its PSF is complex due to segmentation. Accurate modeling is necessary. In spectroscopy, velocity dispersion measurements are limited by SNR and by template mismatch. Stellar population models used to infer stellar mass have uncertainties. Comparing dynamical mass to stellar mass can reveal dark matter, but those comparisons must include uncertainties. Detection of gravity beyond luminous matter is therefore a statistical statement. Webb's improved data reduces uncertainties. Now, to maintain the requested tone, keep the narration observational and serious. Stay away from hype. Avoid addressing the viewer. Continue as a calm explanation of measurement. In a processed Webb image of a lensing cluster, the foreground mass distribution is not visible as a single object. It is a field of galaxies and diffuse light, yet the arcs trace the potential. Each arc is a path solution. The arc's curvature radius roughly indicates the Einstein radius. Multiple arcs at different radii correspond to sources at different redshifts. With spectroscopic confirmation, each arc becomes a constraint on the potential at that radius. The mass profile is reconstructed over a range. This is gravity detected as a radial function of projected mass. When the lens is at high redshift, the arcs may be faint and red. Webb's sensitivity makes them detectable. That extends gravitational mapping to earlier times. The object's gravity is detected in the sense that its mass profile is measured despite its distance. Now add one more layer. In cosmological lensing, the metric potentials evolve with time. Photons crossing evolving potentials can gain or lose energy, integrated Sachs-Wolf effect. But that is a CMB-related topic and would drift. Avoid. Keep to lensing and dynamics. Instead, focus on the fact that the lens potential is at the lens epoch. The mass distribution inferred is the distribution then, not now. Therefore, detection is a measurement of gravity in the past. The object's gravity is detected as it was. This matters because the object may have evolved. Webb's observations are time delayed, but this is still within topic because it clarifies what is detected, the gravitational imprint of a distant object at a specific cosmic time. Now, One might also consider that gravity can be detected through structure formation signatures in the distribution of galaxies, but that becomes too broad. Keep to specific observational signatures in Webb data, arcs, multiple images, spectra. So proceed to dynamical measurements at high redshift. Webb can observe rest frame optical emission lines like H alpha, O3, etc., redshifted into infrared. These lines trace star-forming regions and gas kinematics. Spatially resolved spectroscopy can map rotation curves. A rotation curve, V of R, implies enclosed mass m,